Hi everybody, here we are. Who would have thought? But this is the way it is, so let's make the best of it. Let's do Chapter 7, Central Limit Theorem. Okay, so this is just the main points. The entire set of the slides is in the files of our Canvas course. If you have any questions or need any help with this, please just email me. And this is a shorter chapter, so the lyrics assignment is shorter, and the Chapter 7 handout is shorter. So not as bad as Chapter 8. Chapter 8's bigger, but that will come. So anyway, what is the central limit theorem? When the population that we're pulling the data from is not normally distributed, we can still use all of our normal distribution tools if we use the central limit theorem. What it allows us to do is approximate this normal distribution. And we can do that by taking samples from the data, calculating the sample mean, and then we make a distribution of that mean. Pretty crazy. So the idea is that we're going to draw these samples from the underlying data, and as you keep drawing them and calculating their mean, we are going to have this normal distribution, and it's a normal distribution of the sampling means. So it's this long thing called sampling distribution of the sample means. And all that it means is that we've taken our underlying data and turned it into a format that we can use all of our normal distribution, normal CDF, inverse norm tools with. There's one thing we need to adjust, and that is that we need to have this new thing here. So the mean is going to stay the same. The mean of this sampling distribution of the sample means is going to be equal to the mean of the population. So, you know, when we drew our normal curves and we would have a mean that was in the middle and it's symmetrical, 50% on one side, 50% on the other side, the mean of the population is still going to go there because as we draw all those samples, they're going to eventually have a sample of the sampling means that is the population mean. Yeah, that's really deep or weird or bizarre or too much to handle. But maybe just be a practitioner and realize we're going to use our normal tools, but we do have one new thing, and that is that we need to adjust the standard deviation to take into account that we're doing this sampling distribution of the sample mean. So what do? We use our usual standard deviation and we just divide it by the square root of n. That's all that we do, square root of n, and then we call it the standard error. So now when we plug into our calculator, rather than doing mean and standard deviation, we're going to do mean and standard error. Not too bad. Okay, so let's do an example. A certain brand of tires has a mean life of 25,000 miles with a standard deviation of 1,600 miles. So we don't know if this is a normally distributed data set, so we're going to do our central limit theorem, which allows us to do our tools. And we're going to do the same types of things where we want to know the probability, that something is greater or that it falls into this part of the distribution. So what's the probability that the mean life of 64 tires is less than 24,600 miles? Okay, so we know what the mean is, 25,000. We know what the n is, 64. We know what the standard deviation is, 1,600. We need to adjust that to make it a standard error, right? So let's take a look. What do? Like I said, we set the mean equal to 25,000. That was the population mean. That's going to be what's in our distribution in the middle. What's our standard error? The 1,600 miles, standard deviation, divided by 8. Divided by 8 because that is the square root of 64, correct? So we have our standard error as 200 miles. Okay, so now we can use our usual tools, right? Same process, like I said, here we go. We just use the standard error. So we use our calculator to determine the required probability. Remember how we were doing this? We wanted to know what's the likelihood that there's less than 24,600 miles, so the probability that our x is less than that. We just think about drawing it again. So here's the 25,000, we have 24,600, sorry, I don't know how to do it on your end. It's going to be lower, and we want to do less than that. So our normal CDF, lower bound, -1e to the 99, upper bound, 24,600, because that's the problem, mean, and standard error. And what do we get when we put it into our calculator? 2.28%. And that is telling us that 2.28% of the sample means will be less than 24,000 600 miles. So hopefully this doesn't feel too bad. It's the same process we were doing in Chapter 6, just recognizing that the underlying data isn't necessarily normally distributed, so we use the Central Limit Theorem to help us use the standard error, which makes the adjustment so that we can use our usual tools. Okay, let's try another example. Okay, another example. In a recent study on the Flurry blog, the mean age of tablet or iPad users is 34 years, and the standard deviation is 15 years. The N, the sample size, is 100. Okay, so let's go ahead and just be able to use the Central Limit Theorem. The mean is still going to be 34 years. We just need to calculate the standard error. So that would be taking what the standard deviation is, which is 15, and you divide it by the square root of n, which is 100, so that'd be 10. So our standard error is now the 1.5. Okay, let's get a question in here. What is the probability that the sample mean age is more than 30 years? Okay, so look down here, that is looking at the probability of getting an x that's greater than 30, and think about it again, we have as our mean 34, so we're going to want the area above 30, and so 30 is to the left of our mean, so that's going to be our lower bound, 30, so we're going to have a positive 1e to the 99 as our upper tail. Oops, sorry, didn't mean to do that. Oof, getting used to this. 34 is our mean, and our standard error 1.5. When you put that into your calculator, the normal CDF, you should get 99.62% of the data would be above 30 years old. So 99.62% of the people using this blog, tablet users, excuse me, are older than 30. That's pretty interesting. Let's keep going, okay? We also can do inverse norm with this. Remember, if you're given an actual data point and asked for the probability or the percentage, that's calculating the area under the normal curve using Central Limit Theorem. That would be normal CDF. But if you're given a percentile or a percentage and you want to know the actual data or z-score, you use inverse norm. So what if we wanted to know the 95th percentile for the sample mean age? Okay, so we go ahead and we put in inverse norm, 0.95, there's our mean age, 34, there's our standard error, 1.5, and what we get out is the number of years back into data. So 36.5 years is the mean age for the sample. We're 95th, that's the 95th percentile. Okay, what's weird is you guys can't ask questions as I'm doing this, so I'll try to go slow enough for you to get it all, but of course you could pause and rewind and watch again. I'm sure that sounds exciting. Okay, last thing, we can also do this for proportions. So a mean is an actual data point that's not in a percentage term, but we could do this for a proportion, which is just a percentage. We had these same types of differentiations when we were calculating standard deviation. We would do it for, the actual data, and then we would do it for percentages. So here we can do the same process for proportions. We're going to, oops, sorry about that, guys. Sorry. We're going to use the sampling distribution of what's called p-bar, and that's just p with a little bar over it. It's akin to x-bar. It's just the mean of our sample, the proportion that's the average proportion for our sample. I can't get a little bar above it sometimes. So what we're going to do is we can calculate what the expected value of our p-bar is, and that's just going to equal our proportion from the population. That's the mean. Excuse me. Sorry, I don't know why I keep doing that. And then, I don't know if you could see this, here's the standard error calculation for the proportion. So like if you have an exam, you'd put this on your formula sheet. In order to do the standard error for just a regular mean, using the Central Limit Theorem, remember we took standard deviation and divided by the square root of n. Now we're taking p times 1 minus p, which is q, and dividing by n and doing the whole thing square root. Sometimes people get that wrong and just do the top part by the square root. Okay, so this is really the only difference, making sure that we have a standard error of the proportion. Let's do an example. Suppose that 72% of prospective job applicants want to have housing nearby, and we want to know what is the probability that a simple random sample of 30, so there's our n, job applicants, will have more than 75% of the job applicants wanting housing nearby. So this could be good for, understanding how you can recruit people, look for where you should locate your business. You can see how this would be helpful for budgeting. What do? You just need to calculate the standard error of the proportion and then do normal CDF. Use our same tools. Okay, so this is a little bit hard. I couldn't get it in the right format, but remember, the proportion of our population is 0.72, so there's our P, times 1 minus P, that whole thing divided by N, and then take the square root of it. And I got for my standard error of the proportion 0.082. So now I go back to the question, what's the probability that you're going to have more than 75% of the job applicants wanting housing nearby? So 0.75 is my lower bound, positive 1E99 is my upper bound, 0.72, that's coming from the proportion of the population, and then 0.082, that's my standard error of the proportion. And I got 35.72%. So that's the answer. 35.72% is the amount of people, job applicants, who want to have housing nearby. 75% want to have housing nearby. And lastly, we can also do proportion as an inverse norm. Okay, same type of thing. We can use our inverse norm if we're given a percentile, and then we want to see the mean number for that. So what's the 90th percentile for the mean stress score for 75 students? So what do we do? 0.9, 3, 1.5 square root, 3.2 students. That's how we could do that one. All right, you guys, that's everything, I think, for Chapter 7 that you need to know for the lyrics and for your handout. Thanks for listening, trying to keep these short and sweet. All righty, email me if you have any questions. Bye.